Okay, good morning again. Welcome to another session for our AI class. And today I want to continue the topic of regressions. So recall from last time that we're trying to build the model that can predict number instead of classes. And then we went through, I guess, the linear type model. We went to the linear regressions, which is essentially just fitting a line through the data. The scikit-learn model allows us to build, a simple linear regression where we only have one x, or multiple linear regressions where we have a lot of x's, a lot of x. Okay, and then we move on to the polynomials model, which is allow us to make a nonlinear function fit to our model, and we use the data, which is a house price data. And we can show that by using the nonlinear model like polynomial fit, we can increase the values of R square, which is the higher the better, or we can reduce the error. We can do MSE, the mean squared error, or there are other types of error, but we're not going to talk about it this class. So we end up with the polynomial regression, which is just another ways of doing the linear regression. It's just that we have the x that can be expanded into multiple features. So x squared, x to the cube, and then, but in the end, this is just another linear model, right? So linear model is something that I would encourage you to use first, even polynomial model, because it's very simple, and then it has a lot of benefits in terms of statistical analysis. You can do a lot of like a confidence interval on that, and then I think it kind of translates well into production because it's so simple. But if that's not enough, then you might want to consider something like support vector regressor, which is also one of my favorite models because it's so powerful but still lightweight enough to do a lot of tasks. Okay. So in order to explain SVR, support vector regressor, I want to go back to linear model again. Okay, so if you recall, in our classification, there is a model called support vector machine, and that model is essentially a linear model, but it has the concept of margin. So what it's trying to do is it tries to maximize the margin so that your dividing line is always going to be in the middle between the two classes. Okay, let me just go back so that I can make that connection to you. Let me just pull this up real quick. Okay, so when I talk about support vector regressions, so this is classification. Support vector machine. So that's for classification. For example, we have two sets of class, the data from two classes, and what the SVM try to do is to draw a straight line such that the line has the maximum margin. So the margin is the distance between the line and the class and one of the data points that are closest to the line. So this is the margin, right? So the line that is best is the line that maximizes that margin. So, and if I were to go into a little more detail, I view this as the street. This is like a road, right? And this is the line that divides the road. So the way that I always talked about it is that we want the road to be as large as possible without having the point that are lying on the road. So the points have to line along the edges like this, but then we try to find the road that is the largest road. That's the margin. And with that algorithm, what you end up with is the line that's actually trying to divide, for example, this line, it's trying to do something like this, which kind of makes sense intuitively, okay? The same thing kind of applies to the support vector regression. So this is the class, right? But then we go to the number. So let me go back to the regressions, okay? The regression is the same thing. Instead of linear regression, which is a straight line through the curve, through the data, right? We're trying to have a concept of a margin. So think about this as another road, right? But this time I want the road such that that this road can actually capture as many points as possible. So you're trying to draw, a straight line with a margin or a road over your data in such a way that this line actually cover as many points as possible. But then there's also another kind of opposing cost function if you are covering too much. So there is a balance between having a larger road and then having the points that are lying outside of the road. So in the end, the support vector machine is kind of nice because instead of just one line, it's trying to do 3 lines, and then it's kind of adjust the width and adjust the angle so that it kind of maximizes the margin with respect to the other condition. So that's why I like this model, because it's kind of helped me pick the line intuitively with that kind of makes sense in terms of what should be the line that is the most appropriate to describe your data. Okay, so again, this is how what I just mentioned. So it's trying to find the best fit of the line. So the best fit is the line that includes all the points in here. Okay, so and then the width of the line is controlled by this parameter called epsilon. So you can kind of adjust it to make sure your model kind of fits what you want. Okay. All right, so again, with the support vector regressor, you can have a different type of kernel. So if it's just a straight line like this, then it wouldn't be that useful. But the fact that support vector machine can do what I told you, if I were to use the linear kernel, it's just drawing a straight line over your data. But then if you were to choose this this kernel called RBF, so radial basis function, it can transform or warp itself into the infinite dimension space, and then it draws that straight line over that space, and then it transforms it back to the original space so that your decision function or your line become nonlinear. So with this, it's very, very cool because you can have you can have a function that has become very, very nonlinear, but the inner working of the model is actually still linear model. So super nice about this, okay? So that's what we're gonna try today. So I don't think linear kernel is that useful, but if you were to use support vector regressor, try with this one, RBF, that's the default one. And you're gonna see that the function or the line that fits to your data become nonlinear, and it fits pretty good. It's quite powerful, okay? And you can use parameter. There's 2 parameters that you can use, which is C, and that is it's called the strength of regularization. So I guess it's a way to control the penalty when you have the point that are off the road or outside your margin. And then the epsilon is the width of your margin. So you can kind of adjust things around to see what happens. Okay, so this one is a bit, you need to try it out. So let's try it out to see what happens, shall we? All right, so we're gonna go back to VS Code, and I'm gonna go through the code for you. Let me do that. Okay, so we're gonna do SVR, and let's do the lecture.ipynb, that one. Okay. Okay, so I need to import lots of things from the from my utility functions again. Okay, so this one is essentially importing a helper function from the utility folders. And then here I'm going to import the model itself. So the model is called SVR, so support vector regressions. Okay, but the rest is actually just okay, so this is Panda and NumPy, and this is for splitting the data. And this line is just the function that I wrote myself. It's actually in this folder right here, S00. Okay, so let me just run one more time to make sure that it's loading. Okay, it takes some time. But it's working. Oh, that's surprising. It takes quite a long time. Okay, done, loading. Okay, so the first step is to load the data. So this one is the same as before. We're gonna load the data called the housing data. And this one is situated in S00 and housing data. If you guys want to take a look, just go there and just click through the data. Okay, so I'm gonna load it right here. And again, if I just take a look at it, df.height, just to remind, okay, so these are the attributes of the houses. And I think we're gonna, our Y value is MEDV, so that's the house price times $1,000. And the X value that we're going to use is called LSTAT. I don't remember what it is, but we choose 1X so that we can visualize it more easily. So we're gonna do the function, predicting MEDV as a function of LSTAT, okay? So we are going to extract the data that we want, so df, right? And then we're gonna do the column called LSTAT. Because we tested last time that this column actually correlates the most with MEDV, and that's why we choose this one, okay? So that one, I'm gonna do another brackets, and then I'm gonna do values. So this is a way to extract the values. This one is the X value, so I'm gonna store this as X variables. And then Y is the answer. So I'm going to do MEDV, okay, dot values, okay. Just to remind you guys the difference between these two syntax. As you can see that when I extract the X value, there are double brackets in here. But when I extract the Y value, there's only one bracket, okay. If you're wondering why this is the case, it's because when you have the X value, it's supposed to be like a matrix. So it's supposed to be 2 dimensions. So that's why I do the double brackets. Even though you only have one column, but the input to the model is expecting a 2-dimensional array. So that's why I do this one. But then for the Y value, it's expecting a vector. So this construction gives you 1-dimensional array. Okay, let me just show you you can check that pretty easily. So x.shape, and you can see that there are 2 dimensions, so 506 rows and 1 column, so 2 number, 2 dimensions. But if I were to do y.shape, that means that this one is only 1 dimension. So only 1 dimension is a vector with 506 elements in it. Okay, so that's why the syntax are different. Just want to remind you guys, maybe looks like typo, right? But it's not, okay? All right, so we got the data, X and Y. The next step is we're going to split the data in train and test. So we're going to use the function from scikit-learn, which is train test split. And we're going to split 0.3, 30% for testing, and then 70% for training. Okay. Okay, again, instead of writing the parameter by like changing the parameter each time, I want to store all the things that I want to do in here. So this one, it's a large dictionary, okay? But what I do in here, I want to experiment with different kernel. So I can have kernel to be linear. I can have polynomial kernel. So the kernel, again, is a way for the model to warp itself, change the space into multi-dimensional space so that it can draw a straight line in that space and come back as the nonlinear function. So with the linear function, this is the linear space, but you can have polynomial space and also RBF, which is one of the most powerful, I guess, kernel that people usually used, okay? And within each of the kernel, there are things that you can change. For example, for the linear kernel, you can change the value of C. But polynomial kernel, because it's the polynomial, so you can have the degree. So you can have 2, 3, 4, and 5, and you can experiment with that, right? And also you can do the RBF kernel. okay? For the RBF kernel, you can do C, which is the strength of regularization, which is like how bad is it if you have the data outside your margin, okay? And epsilon is the width of your margin. So what you can do, so what I want to do, I want to show you a different type of value. For example, I want C to be going from, I guess all C is 1 and 100. And I vary epsilon from 0.1, 1, 10, 100, something like that. Okay, so when I write it like this, it's nice because I'm going to run all the model at once with different sets of parameter, and I can kind of collect all the results and see what effects does the parameter do to your model. Okay. Okay, so I'm going to run the whole thing. Okay, again. If I want to extract anything from the parameter, all I have to do is do param set, and then I want to choose the name of the name of the experiments, like L1, for example. I can do L1 like that, and I get the parameter, right? If I want to do R5, that's how I want to do. So that's the way that I construct, like different types of parameters and different type of kernels too, okay? So what I want to do here is that, let me show you how to do just one experiment, and then you can see how I did it in the loop, okay? So if I want to experiment with just one experiment, just one set of parameter, so let me just choose one. So I want to do, params, right, equal, param set. And then I want to choose L1, which is the linear kernel, okay? So I can print param in here, right? I guess I should do param with S because it's a lot of parameters, right? Param, okay. Right, so right now I want to construct my model with this parameter, okay? So in order to do that, I want to instantiate the model. So the model is going to be equal to SVR, right? If I were to do this, then this one takes in the default parameter, right? But what I want to do is that I want to input the parameter, for example, kernel, it's going to be equal to linear, and then the C value is going to be equal to 1, right? So if I were to type it manually, I would do something like this, kernel equal linear, and then C equal to 1. So that would be the way that I can write it manually. If I print the model, you can see that my model has this specific parameter set written to it, right? But then I don't want to do this manually. Okay, let me just go on. Okay, so I have the model, right? And once you have the model, then you can fit the model to your training data. So I'm going to do model.fit, okay? And when you fit, make sure that you have X train and then Y train, okay? Again, we don't do standardization here because we only have one X. But last time I showed you that if you have multiple X's, you should standardize your data, okay? Okay, so once your model is done, I can make a prediction. So Y predict, right? I'm going to do, okay, Y train. So I'm going to predict the training data. So model.predict. And I can input X train into it. And I also can do the prediction of the test data, which is the model.predict, and then X test, okay? And again, I can use that results to basically calculate the error, okay, and the R1 MSE and so on, okay? I can do that manually, but I already wrote all of that into my, into my helper function. It's called store the results, right? So this one is a function that I store everything in the data frame so that I can output it in a nicer way when I run a lot of model. So I guess this one doesn't work in this because it needs the result. Okay, so if I want to make sure that it works, I need to do this. I need to do results, okay, equal empty, okay, and then what I want is this one, okay, it's gonna store everything in the results, right, and then the model name is something, I can see like linear model, something like that. Why is it like this? Oh, because it doesn't need F string, I can just do something like this, okay. Yeah, I think that's it, parameter. Okay, so I can do params in here. Okay, with S, okay. That's how I store the result. So if I were to look at my results, okay, I can see that I have all the results stored in here. So that's just a function that I wrote to make my life easier. And then I can also plot it. So I can do plot, rec. Again, this one, it's just plotting. It's a function that I wrote to plot the results. You can kind of see what it does in the util folder. But essentially, I can just input all of this into it. Let me show you what happened. Okay, plot rec, okay, and just input everything in here. Let's see what happened right there. Okay, so this is my flow of operation. So I'm gonna construct model, train, calculate the result, the predictions, and then store the results and then plotting it. Okay, but I don't want to do this manually. I want to automate all of this. So what I can do is that I can put this into a loop. So I can do something like this for, right, name and values. So I want to change the parameter. So param set, right, param set dot item. Okay. Okay. So let me just show you what happened here. Okay. If I were to print out name and values, you can see that now I have different name, which is the model name, which is what I call it, and then also the parameter that I want. Okay. Again, I'm gonna start doing this, which is I can do this, which is extract the param, but then the param here has to be name because the name it keeps changing. So make sure that this one is this one. So I extract the parameter, right? Next step, I want to do this. So model equal SVR. But then again, I don't want to hard code this thing. This thing needs to be calculated dynamically. So I can do something like this. I can expand the param, okay? Because this parameter is a dictionary, so the similar things, you can kind of expand it into the keyword argument by using the double star. So that's what I did in my code, right? I guess, but I can do even better than this because actually the value itself, it's actually the same thing as param. So I don't even need this one. I can just do value. So that's what my code is doing. It's doing the same thing because param is exactly what the value is. Because when you do param set.item, the value is the parameter that I want. So that's the reason, this one, right? Okay, so next up, same thing. I can do model.fit, right? And then this is gonna go through all the model, okay? And then this one stay the same. I don't need to change anything. I'm just moving it into my loop like that, okay? And this one also the same. I can store the result in my helper function. I'm gonna move it here, okay? But the only thing I wanna change is that I wanna change the name such that it kind of reflects what the model I'm using. So I'm gonna use the F string and do SVR with the name itself. So the model name it's gonna keep changing so that when I look at the result, I know which one I'm looking at, okay? And the parameter here is the dictionary that contains the parameter. So this one I decided myself. So you don't need to, it's not really a convention or anything. I just designed it for my own use. So this one, I need to input the parameter. So I'm gonna use values. Okay, because the value contains the parameter itself. It's a dictionary that has the parameters. And then I want to plot it. Okay, so I'm going to do, wait, not here. I want to do it, wait, not here. I have to do it outside. It's going to be here. Okay, like that. Okay, so that's it. So I can, the way that you would construct something like this is that you do it manually once. And then you kind of figure out, okay, if I want to loop it, like how do I do it? So that's kind of the process that I went through already, like when I was doing this for you, okay? Okay, let me run it. Okay, you can see a lot of plots in here, but let me also input everything into the data frame. So before I do this, like the end, if I don't plot anything, let me show you this. If I do results in here, my results is actually my result array actually contain the dictionary with all the information that I store. So I actually want to construct the data frame from this because I can see it as in a table. So I want to do pd.dataframe.from_dig. So this one is special because if you have the structure of your data as the array of dictionary, you want to do from dig, okay? So this is kind of a little bit detailed, but I can do something like this. And I want to do df equal, and then I want to display df, okay? So this one is particularly nice because now I can kind of go through all the examples, all the experiments, and then I can see what it's doing in terms of, you know, the performance. So MSE, which is the mean square error. So how much is the error? Square, and then square rooted, okay? And then I want to check out the R square. So in each of the matrices, there is one for training and one for testing. So we have 4 matrices, okay? So what you want to look at in the end, you want to look at the test data, but I just plot the training data just for you to make some comparisons. And again, for all of these experiments, I kind of keep all the parameters so that we can kind of relate back to see what happened, okay? So let me just run it real quick with all the plots, okay? Okay, so let's see what happened, okay? So first, the first model, it's a linear kernel. So think about it as similar to the linear regression with the concept of margin. So a little bit better, but probably not the best function that we need is right here, okay? So as you can see that for our linear function, it's okay during the middle parts, right? But then I think the data on the left, it's a bit, you know, you need the nonlinear function to cover this one, okay? And then for the next 3 graphs, this is the polynomial kernel. So as you can expect, it's going to be a little bit more nonlinear. So as you can see that. So this one is 2 degree. So with the 2nd degree, then you don't have much flexibility. But for the 3rd and the 4th degree, so I guess polynomials kernel, it's actually not that good, right? And then, but then the rest of the fitting from the, I guess the 5th one to the 9th graph, it's this RBF kernel. So this is where you kind of go into the infinite dimensional space to fit your data and then come back, right? So this one allows a lot of flexibility with increasing epsilon, by the way. So I'm going to create increasing epsilon, which is the width of your margin, okay? So let's see. So RBF. As you can see that it looks a lot better, and right off the bat you can see that the function kind of, you know, become very, very nonlinear. If you want to do a function like this in polynomial fitting, you have to use a lot, many degrees, maybe like 5 or 6, but that's kind of too much in terms of, you know, I guess the terms that you need to use. So it's pretty tedious. But for SVR with RBF kernel, I think it did pretty good job right off the bat with just RBF kernel. So I think that's why this one is pretty powerful. And as you keep increasing epsilon, you can kind of see that it does change. It does change I guess the shape of your curve a little bit. So if the epsilon become too large, then maybe your curve is kind of smooth out a little bit more, okay? And if it's too large, then it becomes just a straight line. Okay, so maybe tame your epsilon value a little bit. Okay, and I guess I want to show you the last one, which is the strength of regularization. So right now I keep C, which is the regularization strength. So this one, if your regularization is small, then I mean if C is small, then you don't allow your model to wiggle too much. You keep the weight to be low in value. That's the concept of regularization. But if you increase your C, that means that you allow the model to experiment with different weights in your model. So, and as you can see that if C equal to 100, then I guess your curve become quite nonlinear, and it has some, you know, like sharp turns in here. And it actually describes your data quite well in terms of the training data, as you can see here. So as you can imagine, the last one probably should have the highest R square. Let me just see. Okay, Now it go to about 0.6. Okay, so which is pretty nice. Okay, if I were to recall from my from our last benchmarks, I think we have about I think this one is probably the best one. If I go back to my polynomials one, probably this one, I have to run again. The linear one goes to about 0.5 in terms of the R squared of the test function, but polynomials go to something like yeah, 0.64. So that's something. So here for the SVR, I remember which one, this one here. So I guess so SVR goes to about the same R square as the polynomial one, but the polynomial fitting, you have to go to about like 5 and 6 degree, which I think is it's a lot. So think about this. If you go to 5-degree polynomials, you're gonna have 5 times your data. So for each x, you have to expand each x into 5 columns before you do any fitting. So right now we only have 1 x, right? But then we have to expand to 5x in our polynomial model. If you have 10 x's in your polynomial with 5 degree, you're going to have 50 columns going in your data. So that's a lot. So that's kind of, I guess that's wasting your memory, basically, right? But with a support vector regressor, you can pretty much just input just 1x. And then the radial basis function actually do a pretty good job as long as you adjust your C and epsilon accordingly. So it's pretty powerful. I guess that's one of my favorite models. Okay. So I guess in the remaining maybe you can spend a couple minutes, maybe change the parameter and run to see if you can get better results, right? What you can do is that you can kind of copy this one. For example, you can do like R6 in here. Okay, because I use R because it's a radial basis kernel. And maybe you can change C to be maybe 1000, right? Maybe you can change epsilon to be, I don't know, 0.1 to just change something and rerun it. And it's going to give you the new model to see, right? So this one actually works, something like that. I think I choose that one because I know that I kind of experiment with it before. So this one is even more nonlinear. Like if you increase C even more, then your function becomes too nonlinear, and that might be too much, right? You are trying to fit too much to your noise in your trained data, so that's not good. Okay, so you want your model to be complex enough, but not too complex, because if it's too complex, then it's not generalized. It does not generalize well to the test data. Okay, so hopefully you have have tried a little bit on the SVR. Okay, so essentially you can just construct a lot of training like a parameter sets, and then you see the result. So that's what I would recommend if you were to test it with Python. So try to make a automated way to build your model. I think that would be the better way. Okay. All right. So let me just move on to another model. It's tree regressions. Okay. So as you recall that in classification we have decision tree and random forest. Same thing. We also have the tree regressions. Okay. So the tree regressions is a similar thing as in the classification, because in classification you are building trees by asking questions, and with each question you divide your data into groups. Similar things here, you are asking questions, but for the regressions you are dividing your data and then you're predicting the mean value of the data that got splitted. Okay, so before I go even further, I wanna just mention that in the tree model, it has the same effects. It tends to overfit your data, as you will, I guess, see in the example. Okay, so when I say tree regressions, I mean that anything that built upon the tree model. For example, decision tree is straightforward. That's the tree model. But you can also use random forest, which is a lot of trees. And something that I didn't mention from last time, because to the interest of time, is that there are also models called error boost and gradient boosting. And these are special type of kind of like random forest, but it has some tricks on its hand to make sure that the tree in the forest is actually learning from one another. So it's even more, I guess, even more powerful. So, but again, these are the type that will give you kind of like the tree-based results, as you will see. Okay. So how does decision tree regression works, right? As for example, you have data like this. Okay. What it's doing first is that it's going to calculate the split in your x. Okay. So asking question is just picking the value of x that you want to split. And the choice of that split actually determined from the concept called entropy or Gini. So something that you would, same thing with the classification. So you gotta split where the information gain is maximized, same thing. But this one for the regression type, okay? So let's suppose that after the model is determined the best split, it determined it to be 5.5 right here. Okay, so the model is going to determine that the best split is at 5.5. So as you can imagine that it's going to split right here. Okay, so that is asking the question, like if x is larger or smaller than 5.5. Okay, and for the value that is predicting, if x is smaller than 5.5, what it's going to do is that it's going to take the value of the point to the left of that split and then calculate the mean of it. So the mean of that 3 points is probably going to be this value right here. Okay, so the mean value is a mean value in the y-axis. Okay, so that's how it's predicting the value. So with this split, if x is less than 5.5, it's gonna predict I guess y, the mean, the y1 bar value. Okay, but if x is larger than 5.5, it's gonna take all the value, all of this and all of this, right, and calculate the means, which is going to result in something here, so y bar 2. Okay, so with this model, if you were to use this in your prediction, if you get a new x, for example, like I'm wondering what is the prediction of this x right here, so maybe x1 prime, right? What it's going to do is that it's going to use this line, which is going to go up here, right, and then it's going to answer y bar 2. So that's the tree model. It's so simple, right? And it's so simple that it should not work. Like if you're thinking about how the model is constructed, like it should not work, right? But it's actually worked quite well and it actually worked too well, actually, okay? So with just one split, it doesn't seem like this model is doing much, right? But then there's nothing preventing you from splitting further. For example, I think this split, it's okay. Like if I were to choose any x in here, I think my y1 bar makes sense because it's kind of close to the data. But how about this guy here? Like this one is still not good, right? And then we can calculate the MSE to determine if it's not good. Like that's something that we can calculate. So let's split further in here, right? So what happened is that it can do, for example, let's focus on this split right here, right? It's something that's larger than 5.5, right? So if I were to circle this leaf right here, it's going to be this leaf right here, okay? So I'm going to split further, but I'm going to go at 12 right here. So think about this line. This line is going to split further at about 12, right? So that's something here. So this is the split 12, okay? And again, when you split, right, you're going to take the value to the left of your split and calculate the mean values of it. So that is something would be this value, 16.25. And then there's another mean value of the data point to the right of your split, which is going to be 4.667. So that's one right here, right? 4.667, okay? And right now you can see that our function looks better. So it's actually going to do another split to the left, right? So even the left leaf from the first split is going to get splitted further at the location x equal to 2 into another 2 means in here, okay? So as you can imagine that if you keep splitting further, you can actually fit your data perfectly. Like decision tree can actually fit your data 100% correct by doing as many splits as your data points. But as you can imagine again that if you do that, you're going to get perfect R1, R square, or 0 MSE in your trained data. But then once you go into your test data, it's probably not going to perform well. It's not generalized well. That's called overfitting, okay? All right, so this is one dimension. But again, and then another point is that the decision tree can also fit the data pretty well if it's non-linear. But think about this. If your data is linear, then this is not going to perform well either, because decision tree can only do step function. But if you have the data that are linear, then you will end up making, like you're trying to fit the step onto the straight line like this, which is probably going to do well. So if your data, that it's linear, then it might be a good choice to use just linear regression. Might be the best way, okay? Okay, and this one is for one-dimensional data, but then once you have more than 1x, then your decision tree, I guess regression surface will look something like this. It's like a box, okay? So something to keep in mind, if you were to use the machine learning model, like a tree-based model to do regressions, you always gonna get like a flat function, step function. Like this one will be a step function in 2 dimensions, but in a higher dimension, it's always gonna be the same. You're gonna get like a flat surface, okay? So this is something that I always kind of argue with students, because like in industrial engineer, we want to do something like this, right? You have data, like when you do DOE, for example, right? You perform experiment like this, right? And then you do like Y and X, right? And then in the process of DOE, you're gonna end up with the kind of like the function, right? Like for example, you do ANOVA, for example, and you come up with like decision surface like that, right? And what you want to do is that you want to find the maximum value. So like once you construct your, I guess, response surface, right? You can maximize that, or you can optimize that surface to find like where is the best value of X. Like if, for example, maybe I can do something like this to show you. Okay, so maybe it's something like that. I don't know, something like that. And if your function is like this, and you try to fit, and it goes like, I don't know, like this, right? You can kind of argue that from your I don't know, DOE or response surface analysis, something like that, the best place you want is here. So maybe your data is like this, I don't know, like that, okay. So, and that way you can kind of say that, okay, if I want to optimize my X, right, this will be my X star, which is like the best X from my DOE experiments, okay. But here's the thing, like this one's okay, like I don't have a problem with it. But then I've seen, some of the projects were doing something like this. So they put all of this into the regression, machine learning regression model, like decision tree or like random forest. And then they do the same process where they try to optimize the model, like find the best X, okay? But here's my problem with this approach because, again, let me just delete the line, or maybe I can just delete this, okay? So let's say you want to fit the tree model, so it might look something like this. So the tree models always give you step function, okay? And in that case, if you use this and you try to optimize this, actually your range of X that you optimize this function for is actually here. So what you're predicting is that your X, like your optimized X, is actually a larger range. And that's because of the artifacts of fitting your decision tree. And that's because, I don't know, because decision trees always produce the step function. When you have the step function, it's kind of hard to do optimization. First, because it doesn't have any maximum. It has a lot of value as a maximum. But the thing is that when you use your algorithm to find the maximum, you're going to use something like heuristic approach, like swarm, particle swarm, anything. It's just going to pick one of this. Like it's not going to give you the range because you don't solve it exactly. You are doing the meta, like heuristic version of it, which is going to give you one value. So it might end up into the fact that you are picking any of this range, like every time you run your model. So your X is actually, I guess, non-deterministic first. And the second one is that it's not even going to be reproducible well because it's just flat function. So there's no minimum, there's no maximum for it. So something to keep in mind, because I always argue with students, like you should not use your, when you want to do optimization from your DOE, I don't think decision tree or tree-based model works. But SVM is okay because it's producing the curve function. Polynomials fine, linear functions fine, but not decision tree or any tree-based model. So something to keep in mind if you were to do DOE with machine learning, maybe come talk to me. Maybe I'll argue with you even more, right? I'll try to convince you not to use decision tree-based model. But I've seen I've seen a student project that do this and then they publish, fine. I mean, if the reviewers fine with me, okay? But in the back of my mind, I always think that decision tree model doesn't work for optimization, for the fact that it's like this. Okay, I hope that makes sense a little bit, and then if you have questions, and you can come argue with me, okay? It will be fun. All right, so let's try it out the decision tree model. I think I only show you the decision tree model and also random forest. Oh, actually, I show you everything. That's cool, okay. All right, so let's do just the first two, because I guess we can do the first four, it's fine. The rest, this one, you kind of need to install additional library, so we can skip that. Okay. Okay, I'm going to do c1.ipynb. Okay, first off, I want to delete this one, that one. Okay. Okay, let's start with decision tree. Okay, so first I'm going to use all of my code to import the utility functions. So it goes here, enter, yes. Okay, done. Next one, I'm going to import all the necessary library. So panda numpy, all the utility functions, but the one that the one that's changing here is called decision tree regressor. So notice the word regressor. It's not classifier anymore. We're predicting values right here. Okay. Next up, we're gonna import the data, we're gonna pick the right columns, and then we're gonna split the data. So all of this can be done in one block. Okay, done. Okay, again, here, this is my method to construct different parameter sets. Okay, so right here, as you might recall, when you're constructing the tree, one of the important parameters to note is the depth. So how many questions can we ask in terms of in a series? Okay, so if you do 1, then that means that you can have 1 split, and 2 splits. I mean 2 split right one after another. And if it's none, then it's gonna keep doing it until it doesn't help with the information gain concept. Okay. This code is a bit convoluted, so let me explain what I want to do. First, I want to show you that in the end, what I want is I want to have a dictionary with key, which is the name of the experiments, and then the value, which is the dictionary containing the parameter that I want, which is called max depth. Okay? So the way that I do here is that I want to, so let's do it here. First, I construct an array. Okay? So this array has, like maybe six things in it, okay? So first I do for, I can say something like I in max depth. So actually not I, but I want to do MD, okay? So if I only do this loop and then I print MD, you might expect, the content of your array to be printed out. And that's exactly what I do. So I wanna be able to loop over the content in the array first. That's the first step that I do. Okay. See, but then I want to construct a dictionary with the keys in it, right? And then the keys and the key needs to change too. So the way that I can do is that I can do something like this. Okay. I want a dictionary called param set, which is empty. Okay. And let me show you this. If I were to construct something like this, I can do param set, right? And then let me just do one. If I do ex0 equal to, okay, another actually I do, okay, equal to the parameter set, which is max depth, right? And then this one's gonna, let me just put it MDs in here. Let me show you what happened. Okay. So this line is saying that I start with the empty dictionary and I want to keep putting in the key and the value. Okay. So if I were to print this one out, let me just show you this param set, right? See the thing here? I only have 1 keys in here, and that's because I hard code this part in. Okay. Right. This one is ex0. Okay. So okay, so maybe I want to show you this one first. Okay, so if I were to do this one manually, I would do something like this. I want to do param set equal. I guess this one's okay. This one goes here, right? I want to do param set of ex0 equal to the max depth of needs to be in here of 1. Okay. And I want to do another one here. I want to do 1, max depth of 2, something like that. So that's something that I want to do. I want to keep doing this with all of the max depth here. But then that's kind of tedious because this one I have to do it manually. So let me put it in here. I don't want to do this. Okay. What I want is I want to loop it. So I'm looping all the max depths in here. I put it into the dictionary. So that one's kind of taken care of, right? But this one is kind of, you need some work on it because I want some way to make sure that the number get increments. So that is the reason that I do something like this. It's called enumerate. Okay, so I don't think I ever told you about this. Okay, so let me just show you what I did here. Enumerate, right? Wait, make a spike typo, enumerate. Okay. Okay, so let me go back here to show you what happened if I do enumerate. Okay, so if I do for, right, I or maybe just do like array, right? Equal, maybe just do AA, equal A, B, C, okay? If I do for A in AA, right, and I print A, then I get ABC. So that's one pretty straightforward, right? Array, loop things in array, print it out. But actually, I want the order, like, or the number that keeps changing every time, so that if I do enumerate AA, what I get is this one. So as you can see that enumerate means that give it a number. Like each time you do the loop, it increments that number. So first start from 0, 1, and 2, right? So what I can do is that I can deconstruct this. It's called destructure. So I want to do this. I want to do I and A. If I do this, I can do I and A. Now I get the number 0 and A, and 1 and B, and 2 and C. So I can use this I to do something else. For example, I can use this one to construct my, my experiment number, for example. Okay? So that's the reason why I want to do this one. If I enumerate this number, I can construct it so that I can do I and MD. But then this one, I can input just the number i's in here. And then now I can have, you know, like the number of experiment that keep incrementing, ex1, 2, 3, and 4. Okay, so that's why it looks kind of convoluted. But the reason is I want to show you the function enumerate, which is kind of useful when you want to loop something, but you need some indication of the number that increments. Then you can use enumerate function. Okay, and you split it out into the destructuring like this, and then use it in your statements here. Okay, so what's nice about this is that I can come up with different you know, value in max_def, right? I can do 7, 8, 9, 10, whatever. And when I run this, I get all the parameter set without having to redo anything. Just keep changing it in here. So that's the beauty of doing like a loop like this. Okay. Okay, so I'm going to go back into maybe 6 is enough. Okay, so I got all the parameters in here. And the next is the same because I guess I'm looping, right, through the parameter sets again. So that's equivalent to the code from last time. So I do decision tree regressor, but now I'm injecting the parameter, which is the depth that keeps changing, and then fitting, predicting, store the results, and then plotting the regression curve for you, and then just checking out all the records. Okay, let's run it and see what happens. Okay, as you can imagine, decision tree always gives you step function. So the first one, as you can see, that the first one is where the max depth equal to 1, so 1 split. That's why this is your regression curve, which is pretty bad, right? But now you can keep increasing your split, right? It's a step function basically. Okay, so check this one out. Like as you know, when you increase the max depth even further, now you can kind of see that it gets crazier. And if it's like this, maybe it's not a good idea, right? You want curves that are actually a little bit smoother. Like the one that's like go ups and down like this, probably not the best one, right? I mean, it's probably the best one in terms of fitting to your training data, but probably not the best one in terms of generalization to the unseen data. Okay, like this. This is none. So as you can see that if I set it to be none, then it's going to cover everything in your training data. Like it can describe all the data perfectly. If you go back to your R-square, you can see that this one, pretty good. Actually, it's not like, it's almost perfect, but 0.9. But don't let this one fool you, right? Because this one is the training data. You're fitting to your training data very, very well, right? It keeps increasing. But then look at how it generalized to your test data, right? It's actually maximized as about max depth equal to 3. But then after that, it's actually diminishing return. Like the more you fit to your training data better, the less it fit to your test data. And that's the concept of overfitting. You're fitting too well to your test data. Okay, so keep that in mind. Okay, that's kind of important to know that you don't want your model to be like this. It's called overfitting. Okay, so I guess if you want, you can change other parameter. For example, you can change your max depth, right? But I already showed you the one with none. But you can change it to be something more, maybe like 6 or 7 to see if it's helping or if it's actually not helping. Okay, you can rerun again. Oh, this one missing comma, like that. Okay. It's actually not helping. It's actually even, I mean, I guess it's, I guess it kind of peaks around max depth equal to 3, and apart, and further than that, it's probably not, it's not helping. Okay, so that's something to keep in mind when you use decision tree. Like the tree probably should not be too large, I guess. And if you're curious into what other things you can change, you can kind of see from decision tree regressor, scikit-learn. Oh, not this one. I want to do this one. Okay. Of stable release. Okay, here. The best bet is just copy the name of it. Okay, let me show this one. Okay, so that's the one that I want. Okay, so there are a couple of things that you can do. For example, you can do like min sample split. Right? Same thing. This one is if you have less than this many data points, no splitting. So if you can increase this one, then it's gonna limit the number that you can split your trees. Max depth is probably the one that affects your performance the most. Probably that one. The rest is kind of very, very detailed. So that should be it. I guess max depth is the one that you want. Okay. And the cool thing about this is that once you have the tree-based tree-based model, you want to change it. All you need to do is actually just change the import. So let me show you this one. If I change this one from this decision tree to the random forest regressor, it actually works, like here. I'm importing this, right? And I only change this one, and then come back to the here, and then change it here. It actually works. Let me just run it out. Just change one line, and you can change the model like that, right? Okay. Pretty cool, huh? But for you guys, if you want to try, I can kind of go through the one with random forest, okay? The one with random forest, again, the forest comprises of lots of trees. So the idea is that you want to avoid overfitting. Basically, you don't want your model to fit the training data too well. So you want to have a lot of stupid trees that give you prediction, and you're going to vote it. Make the majority voting. So that one gives you more robustness, okay? The code is actually the same. I only change one thing, which is the imports and also the models in here, right? But again, for the random forest, you have the choice between how many trees you want in your parameter. So this one, actually, I only do max depth, but you can also change your parameter so that you can experiment with different number of trees in your forest, okay? But let me show you what how it works first, right? You're gonna see the change in your regression lines. Okay, as you can see that right away, like even if I have max depth equal to 1, right? You can see that my function looks a bit, more like Jackie, I guess, more jacket, because it has a lot of tree that's trying to give you the answer, right? So it kind of overall, it gives you smoother function. Okay, although inside it's still a step function though. It's still a step function, but it's less pronounced, right? When you do max step equal to 2, 3, 4, 5, then it's gonna change right here. So this one, I think this one looks pretty good, right? And then this one start to get a little more jagged, so probably not the best one. Like here, it start to get you know, a lot of noises in here, like, and then here. And then when it's none, then yeah, like if you have the tree that is none, like a lot of large trees in your forest, it's going to give you a lot of like weird looking curve like this, which is probably not a good idea. So I would think, you know, from my experience that something like this is probably, you know, what you were looking for. You know, although you're not going to have these luxuries in your model, like in your data, if you have more than 1x, right? So you're not going to see this one. But what you can do, so you can check out your R-square, right? Or MSE. You can see that it peaks around max depth equal to 3 again. Actually, this one is doing even better than the decision tree, right? Because it's a bigger model, basically, right? But then if you increase your max depth too much, then you're going to have diminishing return. But again, even if max depth equal to none, like to now, which is a lot of big tree, it still gives you, you know, better performance than decision tree. So I would say that this one probably perform best. So your best bet is to use random forest, okay, than just decision tree, unless you have you know, specific requirement like performance, maybe performance. This one is pretty huge in terms of calculation expense, okay. What I can add is actually, maybe I can show you a little bit more customization. For example, if I were to search for this one in my, in the documents, I can do this one, N estimator. Okay, so the default is 100. So maybe I can write a code that actually generates this one. Okay, well, let's do it to show you how I would approach this. Okay, so I want to change another thing called an estimator. Okay, but I don't want to change only one thing. I want to change a lot of things in here. So I want to do this 100. Maybe I can do 200. 500 and 1000, okay. And for the sake of simplicity, I know already that max depth equal to 3 is probably the best, right? So I want max depth to be the same, 3, 3, 3, 3. See this, okay? I need to have the equal number of it, so I want six experiments. So I want to do maybe 2000. I don't know if it's going to run too long, and maybe that's too much. Maybe I should do 10. Okay. So I want a pair of this parameter. So my max depth is going to keep constant at 3, but now I want to change the estimator. Okay. So I can do something like this. Okay, let me show you how to do this one. Okay, all right. So if I have two things as an array, for example, I have A equal 1, so do A1, A2, and A3. BB equal B1, B2, B3. If I know that I have a pair of things in separate array, right? I can do something like this for I in, but here normally you would put, for example, like AA in here, and you can only have one thing in here, right? You print I and you get A1, A2, A3, right? If you want something in B, then you can have one thing in here. But I want both in my loop, so I think Python has a nice utility function called zip. Okay, zip is like zipper, like you zip things together. So I want to zip two things together, AA and BB. Let's see what happened here. See this? Okay, so I never mentioned this before, but I thought it would be nice to show you that if I have two arrays that has the same length, and then I want to access the elements of each one at a time simultaneously in the loop. I can zip them together, like maybe like do a zipper, okay? And then my variable I will become tuple, okay? So if I want to access the value of A's and B in my loop, I can just deconstruct it like this. I can do A and B. And now I can print A and B's in here. Now I got access to all the values. So, and just to show you further, if I have another value, another array, C1, C2, and C3 is in here. And I can also zip more things in here. And then I can just deconstruct it like this. Now I can have A, B, and C in my disposal. Is that cool, right? So that way, I can go back to my, and I can go back here. And I can do something like this. So I'm going to comment this one out, okay? I want to do for max depth and n estimator equal zip max depth and n estimator. Okay, let me show you this. If I were to print MD and NS, in, not equal, in, like that. Now, see that I get access to the parameter that I want in terms of the max depth and the n estimator, okay? And I can use that to construct the dictionary that I want, okay? So that's a trick that I would use, okay? But actually, but in here, I'm still missing one thing, right? I'm missing the number because I want to construct the key that keeps changing. The key needs some number, right? So let me show you this. I can combine the concept that I just mentioned called enumerate, okay? So I can do another function called enumerate in here. And then I just put it in here. And let me just show you what happened here if I do enumerate zip, okay? I'm going to do I, and then I'm going to do I's in here. See that one? So in here, you can think about it like this. Zip means that it's going to give you 3 things in a tuple. So that's what you get from here, okay? But then if you do enumerate of that, it's going to give you the number. So you get a tuple with a tuple inside, okay? So if I want to access all of this at once, I got to do 4 things in here. So I'm going to do like this. I'm going to do I, and I'm going to do that, A, B, C. So almost like a same structure, right? You want I to be equal to the number. You want A to be equal to whatever inside the tuple, inside that tuple. So it's a 2-layer deep, okay? And now I can print A, B, and C and get access to everything here. That's like a cool trick that I always use. If I need, a lot of things in here, I can just zip them together. And if I need a number, I just enumerate it. But then you kind of have to keep track of the structure so that you can get things out correctly, okay? So I go back to my stuffs in here. I want to do I. That I is going to go into my, and then all the parameters go to my tuple, right? I want to do enumerate one more time, like that, okay? And then now I can print everything, I, and see, I can have my number, I can have my max depth, and I also have my n estimator, right? And now I can go back to whatever I have in here, right? Right here, okay? So this one is the number of the experiments, but then I need another thing called n estimator, which is going to be equal to ns. Okay, and if I print this one out, you can see that I have dictionary with 2 things inside. I mean, each of the experiment has the value of max depth and n estimator. Okay, so that one, it's a lot of things. Like, it looks very convoluted, but if you kind of follow the logic, that's how I would approach it. And now if I do this, then I can just run everything that I want here with a different number of trees in the forest with each tree has the back depth of 3. Okay, let's see what it looks like. Maybe if you want, I can copy this one and send it to you in Mango, maybe. You want to try it out? I think we should have a team or something, Microsoft Teams. Like this one is kind of tedious to use. Okay. This one. And I don't know, I don't have any better place to do rather than this one. Okay, let me just try running it to see what happens, if it's going to take too long. Okay, so that's the work, right? Yeah. Okay, so from my experiments, it's actually the number of tree actually doesn't help. So it's good to know, right? So right now, if it's 10 or if it's 100, actually it doesn't change that much. So 100 is fine. But then going from 100 to 2,000 actually a little bit worse. I mean, I would say that it's the same performance, regardless of the number of the trees. That's what I would say. So it's good to know that I don't need to crank the number of trees up too high and still get a good performance. So that's the thing that you can try it out pretty easily. I mean, I guess you have to code it, but once you get this pattern done, then you can, if you want to do even more parameter, you can, and it's going to keep running automatically. So, just keep in mind, like trick like this will make your life better if you actually have to use, Python, and I guess use one of the strengths in like terms of like automations. Okay, and I guess feel free to use another model. There's a C3 and C4, which those two are the special type of random forest called ADA boost and gradient boosting. So these are the type of forest that, in each forest, the tree can learn from one another. So like in random forest, the trees are completely separate. But for ADA boost and gradient boost, the tree is actually learning from the other tree. It's like learning from the previous mistakes. So then it's supposed to have a better performance. So you can try it out to see if you can, the shape of the line is different, and if you can see a better performance for the regression results. Okay. I think I'm gonna get some maybe 10 minutes break, and we'll come back. We'll finish up with the last one. Okay.